Good morning. Half of you are probably down there. Were there a lot of people down there?
No, there's no one.
Oh, okay.
The door's locked and it's obvious.
Oh, it's obvious. Okay. So going around is a one page for today, a handout for discussion today. It's in a blue folder. We are somewhat fewer than we were Thursday. I guess we may fill up more than we were. There, you can stick this in here. So we're going to discuss a trip to the post office. Another one of these exciting OR probability problems. But anyway, this is context. So just to repeat, the exams have been graded, and as some of you have picked them up, a lot of you have picked them up already, but those who haven't picked them up will get them at the recitation at 1, along with the solutions. So they're being handed out at 1. And if you don't get them then, you can come by my office maybe late in the afternoon today. I've got a bunch of stuff, but after 3 or so, I'll be there again. And I'll bring them to class. I'll bring them to class on Thursday if you haven't got them. So about half have got them already. You'll be at 1. And the plan for 1 is that he'll return the exams and go over the exams. So, I mean, that's the question. If you had problems, it's actually probably, if you had difficulties, if you didn't have any difficulties, you could just take your exam and leave, right? But if you had some problems, it might be worth hearing about it and just going through it, because it's good to get on board. So that might be helpful. So it seems like it's worth the time to go over the exam. Okay, the plan now in this second chunk, we're in between the first midterm and the second midterm, the plan is to do chapters 5 and 6. And that's on exponential distribution, Poisson process, that's chapter 5, and then continuous time Markov chains. And these are all close, all these concepts. Continuous time Markov chains are full of exponential distributions, and so these are really 3 related topics. And actually I'm going to go through this stuff in a kind of, I have a plan that's kind of fast in some way, but then we're going to kind of take it through 2 passes. So my plan is that we actually do chapter 5 in 1 week, and we do chapter 6 in 1 week. And then I start going into some things in more detail, sort of harder topics, because both chapter 5 and 6 have a lot of easy stuff, and so if we go through it, we can go through the main stuff pretty quickly, and then we'll kind of the harder stuff in the second part. So there's like about 5 weeks until the second midterm. And this is the whole, even though we're going to do this 2 chapters at first in 2 weeks, that's all that's going to be covered on the second midterm. So then we're kind of going into deeper things and applications and so forth. So we'll kind of do 1 pass through these 2 chapters in the first 2 weeks, and then extra things after that. Okay. So, in that spirit, I'm going to be, given that this is going to be 2 weeks, I'm going to talk about the exponential distribution today, I'm going to talk about the Poisson process on Thursday, and I'm going to have 2 classes on continuous time Markov chains the next week. We'll go right through the whole thing. But it'll be the easy stuff in those chapters. And then, like you saw in chapter 4, there's some harder stuff and easy, basic stuff. And so we're kind of taking the first pass through the easy stuff. Okay. Well, so the idea here, we're going to do this from one of these problems. We have 5 students from our class are going to go to the post office. They're going to the post office. Is it 113 or 112? And this is unlike when you go to that post office. They're going to go in and they're going to find nobody there. There's going to be 3 clerks. There's 5 of them. They go together. There's 3 clerks in the post office. So there's nobody there. They each go to one of the clerks, and 2 of them are waiting. Right? So this is a queuing model. It's kind of a simple situation. We're not considering it very long. We're just going to look at these 5 students and see what their experience is. How long do they wait? How long does it take them to get through? Who gets served first? Who gets served last? How long does it take for everybody to get served? Just these 5. So you have a picture like this. This is a queuing model, and then this would be the service space, and there's 3 clerks, and then we're going to have arrivals coming in here. But we actually have in our instance, it's not an ongoing stochastic process. We just have all 5 come in at once, and so 1 is here, 2 is here, 3 is here, and then waiting is 4 and 5. And in particular, now you should have this coming around. There's a page that describes this in the blue folder. There should be lots of them, right? Does everybody have this now? Sort of maybe pass some of this around, because there should be plenty, unless somebody feel that they need multiple copies of this page. Okay, so we have Thomas. I guess this is Thomas here. Thomas is Thomas, Nicholas, Segi, Wenki, and Pimrapai. Probably butchered the pronunciation of all, but possibly with the exception of Thomas, which I can handle. But and then I might turn out to be wrong. Okay, so here we are. These first 3 go right in here, and these 2 are waiting. And okay, yeah, we have a surge of arrivals now in our queuing, in this queuing system. Gee, we're filling up. Okay. There is a sheet for new arrivals. There's a sheet describing what we're talking about today. Oh, there's the blue. There it is here. Here it is. Okay. Well, so they're in service. These 3 are in service, and these 2 are waiting. And now we're going to assume that the service times, the time that they're going to spend, the service time for each person is exponentially distributed with a mean of 2 minutes. And they're all independent. So they have some sort of things to do, mailing or getting stamps or whatever, and they have a mean. 2 minutes is a little long, perhaps, but anyway, we're assuming it's 2 minutes. Each has a mean of 2 minutes, these 3, and then as soon as one of these 3 finishes, they leave, and the first one in line goes there. And as soon as that person, one of the next 3, so these 3 are in service, and the first, but their service times are independent, and an exponential distribution is continuous. So one of these people, and only one, will finish first, because there won't be any ties. The probability of a tie will be 0. And when that person finishes, Wenki goes to wherever that person is and starts service. And then there'll be 3 in service again, and the first one done, then Pimrampai will go and start service. Okay. So their service time this is where we get to the focus on the exponential variable. So if we take a Thomas, the probability that Thomas's length of service is less than or equal to t is 1 minus e to the minus lambda t, where 1 over lambda equals 2 minutes. So the exponential distribution, here's the CDF, cumulative distribution. When the exponential distribution is nice and simple, there's a single parameter, this parameter lambda, and the reciprocal of lambda is the mean. So its density, if you wrote the density down, which you've already, or in our case, if it's a mean of 2 minutes, right? This would be like this, because lambda is equal to half. Okay. Okay, you see where this little story was we're going to do chapter 5 this week and chapter 6 next week as a quick pass. Okay. Now, that's sort of the whole thing. All 5 people have the same service distribution. And they're all the 5 service times are independent. We're assuming they all arrive at once, and they start like this, but the 5 service times are independent. And then we want to know what happens, who finishes first, second, how long, and so forth. Okay, well, we start out. Part A, what is the expected time from the moment the students enter the post office until Segi finishes service? So here he is here. He starts right away, so it's the same as any of them, Thomas and Segi. But what's the expected time? What's the expected time until he completes his service? Well, that's just the 2 minutes, right? Okay, I'm just repeating the model. This is typical of one of my exam questions where there'd be some initial part that is so easy that you're blown away and your mind, you really get distressed. It's like the quiz show, who is buried in Grant's tomb, right? And then your eyes cross, right? This was common for, and then you can't, sometimes if it's really easy, you just can't believe that that's the right answer. But anyway, this is typical. Okay, what is the probability that he is still in service after 6 minutes? So we want to know the probability that S greater than 6. Well, we know that that's e to the minus lambda. If I do probability S greater than t, the tail is e to the minus lambda t. But then lambda is 1/2 and t is 6, so that's going to be, right? We're also not too bad. Now we want to know the conditional probability that Segi is still in service after 10 minutes, given that he has not been served after 4 minutes. So we ask probability that this is greater than 10, given that it's greater than 4. What's the probability that his service time is greater than 10, given that it is greater than 4? Well, we know this is the probability that both of these occur, which is just this, divided by this. That's just by the definition. So if we write this out, we would get, we just leave the lambda general. But then if we looked at this, we would see that this is the exponential of lambda 10 minus 4 equals e to the minus lambda 6. So this is another maybe, I guess I'm not wordy, but this certainly okay. What do we want to see here? I guess I haven't written it in a good way. That if he's been in the system for 4 minutes, we're asking what's the probability he's going to be there 10. So we're asking the probability he's going to be there 6 units of time, 6 minutes longer, given that he's been there for 4. And the 6 minutes longer is the same as if he started at time 0. So the property that's, I guess this is good here. I think we can remember this. The property, this one property brings all sorts of stuff. It is totally produces all of chapters 5 and 6, almost everything, is that the probability that t is greater than t plus u, given t is greater than u, is equal to the probability that t is greater than t. Right? Now, we're saying, this is, given that it's greater than some time u, then this much more. So I'm in the before, this would say probability t is greater than 4 plus 6, given that t is greater than 4, is equal to the probability that t is greater than 6. Write down the right thing. Yeah, jump up if it seems crazy. But this is just what we went through here, right? This could have been 4 plus 6. And then because of the exponential, right, the exponential is, this is, the ratio of two exponentials is the exponential of the difference. So because this is this, because this exponential function is this, we get this. Now, this is the easy way. The interesting, so the point this is if I have, well, I guess I was supposed to have S here, right? So it doesn't matter, any of these people, right? It was supposed to be Segi. So if I have an exponential distribution, exponential distribution, then it has this lack of memory property. But this, the lack of memory property, is really crucial. And that's saying that the probability of this increment t, given that it's been u, t more, is independent of u. Now, if you have an exponential distribution, it's easy to see you have this property. The kind of impressive thing is that is the only probability distribution with that property. So you could start off with this would produce an equation. If you wrote this down as an equation and you said, well, that's the tail, so you would have written this. This is, that's what this means, and this would be, so you have an equation that looks like this. In other words, this conditional probability, if we write it down, because both of these events, the intersection of these two events is just this, we have this, and this event is this, where this little FC of t is by definition the tail of the CDF. So if I look at the tail, I have, this is the conditional probability, and here's the tail probability itself. And that produces, if I multiply through, that produces this equation where this function, the tail probability at t plus u, is the product of values at t and u. And that's supposed to be true for all t and u. And that, you can show, is only satisfied by the exponential function. So this is why the exponential distribution is, and this is going to give us the Markov property, because when we want to know how the future depends on the past, lack of memory properties means doesn't matter how long the guy's been there. His remaining time has the same distribution. Right? So if he's been there 4 minutes in this case, his remaining time is going to be 6 more, is the same as if when he started and at any time. Okay, so that's a lot is that. Okay, then you have sort of a less important. So this is supposed to be S, but you're told what's this? So now you're asking, what's the probability Segi is going to be there at least 10 minutes, given that Thomas has been there for 4 minutes? I mean, first it was all conditioning on him, on what's his own experience. Now we're asking him to condition on the others. This is another Grant's tomb question, because we've assumed that these are independent of each other, so this should not matter. So this is just the probability that S is greater than 10, which is again the exponential e to the minus lambda 10, and lambda is again 1/2. Okay. Okay, part E. We're getting there. Now it's beginning to get, well, this is a big deal here, so I emphasize this. I'm in danger of doing this problem in 10 minutes or something. I'm feeling like that. I'm sorry if I'm going Crazy here? Okay, but well, let's see. Now we got, what is the probability that Thomas is the first to complete service? So let me put back, I have to put this picture back. I guess we need this. Maybe it'll suffice to have it here. We have Thomas, Nicholas, Gutu, Segi, then Wenke and Pimrampa in the queue. So now we're asking for E, the probability that, now let's see, what would I write? I guess, let's see, if I wrote this down mathematically, that would probably be good. The probability that the T is the minimum of T, N, and S. Probability Thomas is the first, was that right? The probability that Thomas is the first to complete service. So the first one is the minimum of these three random variables, and so that's this. Okay. Now we got more nice properties of the exponential. It's going to turn out that the minimum of a bunch of exponentials is going to have a distribution that's again exponential with the sum of the rates. And the probability, so if these had their exponentials with rates lambda 1, lambda 2, and lambda 3, here the lambdas are all a half, because everybody has a mean service time of 2 minutes. But suppose they had different means, just for instance. Then this would have been, well, let's call them lambda t, lambda n, and lambda s. This would be lambda t over lambda t plus lambda n plus lambda s. Well, in our case, it's going to be 1/3, which is obvious. If it's obvious, right? They're all three in service. They have the same distribution. It's symmetric. It ought to be 1/3. Right? That's easy case. Three in service, with each with exponential, each independent. The probability that Thomas is the first of the three should be the same as anybody else, and it's 1/3. However, if they have different rates, it's a different issue. And with different rates, well, instantly, if you think of it a small time, you'd think, well, it ought to be proportional to the rates, and that's the answer. And because of the lack of memory, the history isn't going to change. At any time, it's proportional to these rates. Right? I mean, you think initially this is sort of, it's not exactly, the intuition is that if you have an exponential distribution as to how long something's going to happen, it's going to happen starting at 0 at a constant rate until it happens. There's a sort of rate that lambda is the rate at which it's going to happen. And if it hasn't happened in the past, this rate might be thought of, there's a hazard rate, which is the density, let's say h of t, which is the density divided by the tail. This is the density of something happening at time t, given that it hasn't happened so far. And in this case, that's lambda e to the minus lambda t over e to the minus lambda t equals lambda. So this hazard rate for an exponential is just constant. So there's a constant rate lambda of the event happening. And that's true for each of these three. So as long as all of them are active, they all have the lack of memory property, they're all occurring at these rates. So it's totally reasonable that the probability that the t is the minimum is its rate divided by the sum of the rates, which in our special case is just 1/3. So I'm actually, my approach here is to sort of just tell the story, which is not to prove the story, but you'll find most of these details in Ross, and you can look at it, you can think about it. I'm trying to sort of give an intuition and just tell a story rather than to go into too much mathematics of it, but that's a way of thinking. Okay, so this is the general answer here of this, and then in our case, these are all equal, so it's 1/3. Okay, let's see what if F should be asking what. So this is what the natural next question is. What is the expected time from the moment, so from when they started until the first student finishes? Right? What is the expected time until the first student finishes? So that's this minimum, not this, because we said this is the probability that Thomas was the minimum. But we want to know what's the time of whoever is minimum. Well, so the nice story here is, if there are, here we sit and there are three you think of it this way, there are three clocks going on. There are three people in service, and they each have exponential clocks as to when their event's going to run out, right? And there's a question of which clock's going to go off first, and then there's a question of how long it's going to be. It turns out that those two random variables, the length of time and which one it is, are independent, and they each have simple distributions. So first of all, the probability that Thomas is the minimum is this rate. Secondly, the minimum of these itself has an exponential distribution that's the sum of the rates. It's a very simple story, which is only, this story is only true for the exponential distribution, which is why we always assume the exponential distribution as a convenient reference case, because everything's simple. If it's not exponential, which it might not be in practice, the story is not true. But like a lot of things, if you take the simple model that's idealized, got a special story, special structure, it may nevertheless tell you what's going on. So but we can see what this is by just thinking, by looking at it. So we'll do a little math. So we want to know what's the probability the minimum's greater than some time t, and let's assume they have these rates, lambda t, lambda n, and lambda s in general. These are three independent exponential random variables. So the probability that the minimum is greater than t is the same as the probability that they're all greater than t, right? One at a time. So this is going to be probability t greater than t, probability n greater than t, probability s greater than 3. Well, first of all, you would say this. Step one, you'd say the probability min greater than t is the same as the probability as all three greater than t, just straight away. But then you'd write this down because the three random variables are independent by assumption. So first you would write this down, that the probability that the minimum of these three random variables is greater than t is the probability that all three are greater than t. That's just translating what the minimum means. Then I write this down next because these three random variables are independent. So I have this. So I skip this step. Now I have e to the minus lambda t, e to the minus lambda nt, e to the minus lambda st, which because of the exponential is just e to the minus lambda t plus lambda n plus lambda s t, and there we see it. This minimum has the exponential distribution with the rate, the sum of these rates. And the mean, therefore, is 1 over lambda 1 plus lambda 2 plus lambda 3. This is the rate, and this is the mean. So, and it's what you would think. If one of these has mean 2 minutes, the first one is going to be 2/3, because they're, you have three of them going on at once. So the first one is going to be 2/3. So this is, anyway, that's what this is telling you. The rate is a half. So the sum of the rates is 3/2, and the mean is 2/3. So the expected value of min t and s equals 2/3. If you wrote both of these down together, if you wrote this one and that one, you'd see that this event and this one were independent. So they'd be the product. So you'd see that. What the other thing I'm change. So you see here, I'm just derived actually that this minimum has this distribution, which is the rate of the minimum is the sum of the rates, which makes the mean the reciprocal. And since the rate was 1/2 and the mean was 2, we get 2/3. So what is the variance of the time that the first student finishes? So one of the things you're going to see is you already reviewed the exponential distribution in chapter 2. But you're going to really need to know it backwards and forwards, right? I mean, you're going to want to know, well, what is the variance of this time for the first student to finish? Well, we know that this time is, again, exponential, so the variance of an exponential is just the square of the mean. So if this answer that we just got here is 2/3, then the variance is going to be 4/9. So sometimes the questions like this are going to be straightforward property of the exponential distribution, and sometimes they're going to be using chapter 5 where you're talking about several exponentials. Okay, so we now start to think a little bit. Things are beginning to get complicated. We now ask, what's the expected time for Wenke to complete service? Right? So let's think about that. I guess that the thing that time, so I guess the expected time for Wenke to complete write it this long way, but this is equal to this. Right? It's the time for the first one of the first 3 to finish, plus Wenke then enters service and has Wenke's own service time. And this expectation is just this. The expectation is always additive. And this we found to be 2/3, and this is 2. So we have 2 and 2/3. Right? That this we already computed last time, and this is just, once Wenke starts, Wenke's just got the full service time, 2 minutes. Okay. Okay, what's the expected time for all 5 students to finish? Now it's getting a little, now it's getting harder and harder, but we're now asking the expected time for all 5. So let's think about that. Expected time for all 5 to finish. Well, you could think of this in the following way. You could think of how many people are there in the system. And you'd say, well, there are 5. And then there are 4. And then there are 3. And then there are 2. And then there are 1. And then there are 0. Right? So at first, there are 5. But when there are 5, there are only 3 in service. Right? So at the beginning, the first one to finish service, we already saw occurs at rate. Let's just put the rate down. The rate of 1 was 1/2, but this is 3/2. This is the rate. Remember that lambda equals 1/2. The rate of each of these exponentials has a rate 1/2. But at the beginning, 3 are in service, and the time till the first one to finish is going to be exponential with a rate 3/2. At that time, one of these finishes, we don't care which one, and Wenke moves in, and there are again 3 in service. So this is going to again go at rate 3/2. And there's a lack of memory property, so we don't care about the history. So it all starts over. So at this time, we have, when Wenke enters, there are 4 in the system, but 3 in service. And when one of them finishes, Pimrampai enters service. So there's again 3 in service, and it's going at rate 3/2. I mean, this is an exponential variable with this 3/2. And then because of the lack of memory property, this is a new exponential with 3/2. And this is an exponential with 3/2. But now there's only 2 left, right? Only 2 left. We don't know which 2, right? We don't know which 2. But there are 2 left. After 3 of them have finished, there's 2 in here. So since there's only 2 there, the rate is going to be 2/2. 2/2, or 1. And then finally, there's 1 left. So the time for all of them to finish is the sum of 5 exponential random variables, but not the original ones with mean 2, right? If there were 5 original ones, it would be 5 times 2 is 10. But actually, they're not all in service at once, right? So it's first they're 3, and so it's this. So if you think of it, that total time is t1 plus t2 plus t3 plus t4 plus t5, where these 5 variables are exponential variables with these rates. So what's the mean? Well, the mean of the sum of those things is the sum of the means. Right? I'm just taking the reciprocals of these rates to get the means. So I'm constantly using the rate as the reciprocal of the mean, right? The rate is the reciprocal of a mean. These are 5 independent exponential variables with these rates. So the means are the reciprocals, 2/3, 2/3, 2/3, 1, 2. Notice that actually in this total time, this business of the last one is going to take a long time. Whoever it is, the last one is going to take a big chunk of time. I mean, this is 2, and this is 1, and here's 2. So the last, even though there are 5 people being served, the last one, the expected time for the last one, whoever it is 2/5 of the total time. And that's because at that point, there's only 1 in service. So when they're all 3 being worked on, the system is moving through them more quickly. Should make sense. Okay, then the question is, what is the variance of this time? But again, yeah. Good. Be good to have some questions. There might be a general sense right now of major glassing over. Yeah.
Is there a reason why you're doing 5, 4, 3, 2, 1, and 0? Can you have the state where 2 of them finish at the same time? And then
No, because they're independent and they're continuous distribution, they can't finish at the same time.
Because they have separate exponential distributions.
Yeah, they have separate exponential distributions, so they can't finish at the same time. Only one's going to finish. And so, yeah, that's going to simplify. You don't have these messy cases about ties and everything. Can't have, with probability 0, because it's continuous variables that are independent. So there's the ties happen with probability 0. Yeah.
Going back to the expected value of the minimum of Tn and that.
Yeah.
I understand how you got it using the finding a distribution, but why couldn't you do something like the expected value of T and it's the min plus the expected value of N and it's the min plus the expected value of S and it's the min. So like.
But the minimum. You could start calculating this, but you have to be careful what you do, because you could start to do something else. I think it was easy in that context to just say the minimum means that they're all something and go to the distribution and see that it's exponential with the sum of the rates. You can do this other ways. So indeed, almost all these problems can be done in a variety of ways when you're thinking of the modeling. I mean, you don't have to think that way. However, the thing that's going on is that everything's going to turn out to be independent exponential variables. So everything becomes an easy story to answer. When you want to know the mean and the variance and whatever, the distribution of the time for all these students to finish, It's not hard because you can write this down as the sum of 5 independent exponential variables with known means or rates. Right? Here they are. Here's the 5 rates. So what is the variance? The variance of the sum is the sum of the variances provided the random variables are independent, which they are here. And the variance of each one, they're each exponential, so the variance is the square of the mean. So when you want to know, all you're doing is you're putting together really basic properties that are true. So you need to know those basic properties. You need to know that if these are independent exponential variables, the variance of the sum is the sum of the variances. And if this is the mean, the variance is 4/9 plus 4/9 plus 4/9 plus 1 plus 4. Right? I just add the squares of the means. And I'm using the fact that the variance of an exponential is the square of the mean. And I'm using the fact that the variance of the sum is the sum of the variances, which depends, part of that depends on the exponential distribution, part of that depends on the independence. And you kind of, that stuff you're going to use over and over again. And there's 2 issues here. There's 2 issues we're looking at. One issue is which event, and the other issue is length of time. So there was this question we asked at the beginning was what was the probability that Thomas was the minimum? The other thing is what's the length of the minimum? And one is this question of which one is this ratio of rates, and the length is the exponential, a new exponential. So let's come to okay, let me go to, I'm feeling like I'm roaring through here just a tad too rapidly. Okay. Well, let's come to K. What is the probability that Wenke is the 3rd student to finish service? So this is kind of, this part has gotten, so we're getting at the last couple of these are actually should look like you'd have no clue if you didn't start applying these techniques. That's what I'm getting at. If you think, well, what's the probability that Wenke is the 3rd? The probability that Wenke is the third to finish. Well, let's see. So how might we think about this? We're thinking, well, you see, Wenke can't be the 1st to finish. So you don't need to worry too much about that. But Wenke could be the 2nd one to finish. So we want probability that Wenke not 2nd. Right? Now, given that Wenke's not 2nd, we want the probability that Wenke 3rd, given not 2nd. We don't have to worry about first. So this is just sort of a strategy to this problem, right? Probability Wenke is the 3rd to finish. Probability Wenke is not the 2nd. Probability Wenke is the 3rd, given not the 2nd. That would do it. Okay? The point here is that these each have simple stories because of the exponential distribution, right? These have simple stories. So what's the probability Wenke's not 2nd? Well, Wenke sits here, and one of these 3 finishes service at some time. And so Wenke goes into service. So at that point, there are 3. Wenke is one of 3 in service. And the probability that Wenke is the 2nd one is the 1 out of 3, or, it would have been this. If I were not served, would have been lambda 1 plus lambda 2 over lambda 1 plus lambda 2. Well, it's a little hard if they have different lambdas. But in this case, Wenke not served is 1/3. Because when Wenke enters, it's the weight of 1 over the sum of the rates. And each has the same rate. So Wenke not served, 2/3. Not 2nd, right? 2/3. One of the other 2. One of the other 2 is served before Wenke. Now, given that Wenke is not second, everything starts over at that time. So at that time, remember, lack of memory property again. Everything starts over, but Wenke is in service now. But there's, at that time, when Wenke enters service, there's 3 people in service. Now, when one more leaves and the second have finished, there's still 3 in service, right? So we have first completion, second, third. First doesn't matter. So we ignore that. When we're concerned first about the second one, and there's 3 in service, and on the third one, there's still 3 in service. So now Wenke is there because we've assumed that, conditioned on Wenke did not finish. Wenke is one of 3 in service. But now we want the probability Wenke is the one served. So this is 1/3. And it's just the product of these 2. That, I mean, all of this detail is illustrative of what you can do with the exponential distribution because there's all this nice property. If you made these distributions something else, uniform, binomial, anything you want, all these questions would be producing a horrendous mess. You wouldn't be able to do anything. Whereas here, you just write the answer right down. Once you realize it's exponential, you're saying Wenke is the third, probably Wenke is the third to finish. This part is easy, but these parts become easy because everything's lack of memory property because it's exponential. And then the independence means that this is just a product. So this is 2/9. Okay, then you have the final thing, which is a little brutal, is suppose you wanted to calculate the probability that the time required for all 5 students to complete service will be at least 10 minutes. So you're thinking the probability, that was all those times. Well, we know the mean. We know the mean is this. The mean is this 2, but the mean is 5. 2 plus 1, 5. And then the variance is 8/9, 5 and 12/9, right? 5 and 12/9. Variance is 6 1/3. So it's believable that, well, there's some chance that all 5 is going to be greater. The time for all 5 is going to be. Now, this is the 5 times to go down here. So we're back to talking about the time all 5 students finish their service. And we want to know this. Okay, well, now, the question doesn't actually ask you to compute it. It says, suppose that you wanted to calculate that probability of the time required all 5 students to complete service will exceed 10 minutes. What computational tool makes that calculation easy? And why? So what would we do? What do I have in mind here? So we haven't really done this, but we've discussed it. So this is actually complicated, and it comes from, if you just take 2 of them, if you think of the probability T1 plus T2 greater than some T, that this is complicated, as you had a chance to do one of these in your exam, right? If you wrote this down, you would have said, well, let's see, so probability T greater than T, you'd have had probability T1 greater than T minus X, F T2 X, say. So I can I can let t2 be anything. I might as well just go here, right? So t2 can be x, and then t1 is greater than t minus x. This would be the convolution integral of some sort. I mean, I've got a tail here. I mean, depending on whether I write the density or the CDF or the tail, I'm going to have a different convolution integral. And if I proceed actually with this, I'm going to get a 5-dimensional integral. Because this is not sum of 2, it's the sum of 5. Or if I think about this, this sum of 2 produces this integral, and in here is a new one of these tails, which will be, I can represent as another integral, right? If I write t1 plus t2 plus t3 plus t4 plus t5, and I write this t1 plus this thing, and then I do it again and write t2 blah blah, and I repeat this 5 times, I'm going to have inside each integral, I'm going to get a new integral for 5 times. So I'm going to have a 5-dimensional integral. Kind of ugly, okay? You don't really want to do that. Now, instead of that, if you want the transform, it turns out to be easy. So the Laplace transform of this is easy. So this is actually kind of, the point of this, maybe if you're writing any notes, the point is this. There actually will be some notes online related to these notes, solutions. So that there'll be something I've written. You can compare whether what I've written has any bearing to what you've written, or what you think I said. So that's an issue. It's a little unclear. But anyway, there will be written notes online related to this, so it'll help. But the thing that would go with this is if you wrote this down and you didn't write this, you would start to think you needed to know this, right? You'd come back to this later and say, this doesn't look good, and I have to know it. It's a bad news. Okay, but this is bad, not good. Okay? But instead we could do, okay, we've got this bad news. But instead we could say, well, what about instead if we want the Laplace transform of this? Here's the Laplace transform for the sum. So the two sort of facts that we'll do one of them. One part of this is this Laplace transform, where s is a variable here, this Laplace transform will have a simple expression. That's half the story, right? So this is going to have a simple expression, and the other part is once I've got the Laplace transform, I can numerically invert it to calculate the thing. So there's algorithm. I just shove it in I shove it in here. This is answer, right? Just like linear programming, right? The meat grinder, you shove the transform in here and out comes the answer. So sitting there is a computational procedure that if you know this, you can get the answer. Now, that part sort of like there exists, that was one of these optional projects to learn that. But anyway, the issue is, now, the point here is this really simple? Well, remember, because of this is the times of the first guy to finish and so forth from the 5th, I guess this in our picture, remember this was the 5, 4, 3, 2, 1, 0, and we had these times, T5, T4, T3, T2. We could have labeled them differently, but I guess this is when there are 5 people there, 4, 3, 2, 1, 0. So the sum of these times would be the time it takes for all of them to finish. And we had all these rates. This was 3 halves, 3 halves, 3 halves, 1 and 1/2, the rates. The main theme, though, because it's exponential, because of the lack of memory, these 5 random variables are independent exponential random variables. Since they're independent, well, let's do this in some step. In any case, because this is exponential, this looks like this. This is just taking this exponential, and the exponential of a sum is the product of the exponentials. No probability, right? We're just using that property of the exponential. But now, since these are independent, this looks like we can factor these expectations. right? So the expectation of the exponential minus s of this sum of random variables is the expectation of the product of those exponentials, but it's the product of the expectations because the expectation of a product is the product of expectations whenever the random variables are independent. So we've used independence. Now we're going to use because the Laplace transform of an exponential distribution is very simple, just that. So let's see why would that be the case. So we're thinking this, say ti, one of these. This is, by meaning of that, right? So the meaning of this is the expectation of this times the probability density of this integrating, right? Okay, and then this is e to the minus sx lambda I e to the minus lambda I x dx. And then that's lambda I e to the minus s plus lambda I. Right? So this Laplace transform, which I might note as f hat ti of s, which is the Laplace transform of this random variable, is also defined this way in terms of the Laplace transform of this function. And then we just plug in the exponential density, and the exponential density has an exponential that goes with this exponential in the transform. So then you can group them together. And then this is just lambda I s plus lambda I. Right? So the Laplace transform of an exponential with rate lambda I is just lambda I over s plus lambda I. Very nice, very simple. So then when we have this is just the product of these 5 transforms. So you have this complicated thing. We want to know this time for all 5 to finish. You can represent right away it's the sum of 5 exponentials. The rates could have initially been given as 5 different rates. They each could have had their own rate. Wouldn't have made any harder. Calculations would be a little different, but, well, let's see. Is that entirely correct? Maybe not quite correct. Yeah, once you get in here, you may depend on what's happening. This has helped, I guess, in this case. In our case, at any rate, we have these 5. We're going nicely down to these five independent exponentials. So I guess I shouldn't overgeneralize. In this case, 5 to 4 to 3, so forth, everything is nice, and we proceed with the rates. All these rates are 1/2, and we have those rates. So this actually, it's not quite that it doesn't totally, this thing becomes a little bit harder in the general case. Well, I'm not sure I don't think that's compelling maybe that you want to know this, but this is typical of what you can know with the exponential distribution. In other words, once you assume things are exponential, you can answer questions like this. This is roughly the character of what you can do with the exponential distribution. We're not doing this. Notice we're just doing questions about what happens to 5 random variables, right? 5 people. It's a very finite problem. It's not a stochastic process in steady state like the Markov chain. It's just detailed analysis of one of these doing this and so forth. So it's a microscopic analysis of individual random variables, not like a continuous time Markov chain. Well, let me kind of give a little preface to where we're going. We've been doing discrete time Markov chains, and we have this matrix P, and we're going n by n, and you're moving among n states. So you might think of the picture something like this. You have your picture is your, but here the steps are of length 1. So one way to think of this is to think of the discrete time Markov chain where the steps are now not 1 but of random length. And it'll be nice if their length is exponential. So you're kind of moving, instead of moving like this might be we might have states, these 3 states, and now we're doing this. This is intended to mean that every step is of length 1. And so we go from 3 states, we sit here, and then we go here at this point, here. We do something at every time and move around. But instead of that, suppose we do where these times here that we spend in this state are random variables. So now we have some sort of continuous time transitions of this. And what's going to make this nice is if these times here are exponential. So everything in sight is going to be independent exponential variables. And where you go, so you're going to have, we're going to have, instead of this, we're going to have a continuous time Markov chain. And we're going to have another matrix Q, which is n by n. And Qij is going to be the rate at which we go from I to j. So instead of this matrix, which is the probability of going in one step, we're going to have an n by n matrix that gives us the rate of going from I to j. And then when you're sitting in state I, you're going to have potential rates of going to state j. But you can think of exponential clocks. Whenever you're sitting in state I, there's a whole bunch of clocks of going elsewhere. And where you actually go will be the first clock to go off. So it'll be a minimum of a bunch of exponentials. So there'll be a bunch of these Qij's, and the rate of how long you stay there is going to have the sum of these rates over j, because there's a clock for each state you could go to, and they're independent exponentials, and the rate's the sum of the rates. So you could be moving, so you'll be moving here, and there'll be some rate Q1, and there'll be some rate Q2, and there'll be some rate Q3, but Qi is going to be the sum of Qij over j, where j is not equal to I. In other words, this is going to be an exponential variable, and it's going to be the sum of these rates. But it's the same reasoning that we're using in this problem, that we say, well, which one of these is first? It's the sum of the rates. Okay, well, this, I'm having a feeling that this is overload in some point. Okay, you're going to have some considerable time to absorb all of this, like 5 weeks, so don't be blown away. I guess the mindset is you're shifting. There's a shift here that should be clear from discrete stuff, integer stuff, finite Markov chains. You move in discrete time through discrete state. All of a sudden, we start talking about exponential variables, so we've got densities. Everything is continuous variables with density functions and so forth instead of discrete. So you have to shift from discrete to continuous. We're talking about continuous stuff, so there's all these densities. And then the exponential is going to be it's going to have all these good properties. So you're going to be working with the exponential. So that's sort of, the relevance is sort of like problem 2 on the exam, is the kind of thing that you're going to need to do with special cases in this stuff. I mean, something like that in the spirit, because you're going to work with densities. So it's a shift. All of chapters 5 and 6 have to do with continuous time stuff and densities. So you want to think that there's a shift there. But to a large extent, the ideas are similar. Okay. Well, we will talk about the Poisson process next time. hopefully you will find there's a look of slight tired look in your faces but hopefully you'll find that when you sit down to do it, it's not bad, and it's okay. You'll hopefully find it okay.